All right, good morning. So let's see what we have before we talk about the actual stuff. Right, so you have already received my announcement, so that would be just like the midterm course evaluation. So it's completely optional if you would like to do it and get a bonus opportunity, you will have to do it by Friday. It's an early participation. I think so far, just to show to you guys, I think we got about close to 20%, which is definitely promising. So if you really want to have a moment to do it at some point by Friday, the set deadline, please feel free. Otherwise, it's definitely okay if you want to do it. Maybe sometime next week, that's also fine. I will only see the feedback after I submit your grades. So it's totally independent, from what I'm going to do to really calculate your grades. So you don't need to worry about anything. Okay? So that's about the course evaluation. And then for your programming test number 1, if you would like to go over your solution, or you would like to see the actual solution, whatever you like, and more than happy to help you, maybe during my office hour. If it doesn't work for your time, feel free to get in touch. I can also schedule some appointment for you. So I think, of course, you only got tomorrow, Thursday. But maybe if you really want to talk to me about it, Friday or even, Friday, maybe the last day. But beyond that, after your programming test 2, if you want to talk about it, I can also do that. Okay? You just have to reach out if you need it. And assignment number 3, solution about a tree, has just been released yesterday. And you can definitely go over it. I would like to talk maybe briefly about it, just to talk about the idea. Not really about Java specifics. That's something you will have to play with. But I can talk about the ideas and also some alternative solution, which I also got inspired by those of you who actually dropped by my office hour before the submission deadline. And for your programming test number 2, it will be next Monday, around this time, next Monday. And that one there, you can just refer to the guide in the practice test. Okay, for your assignment number 3, let me talk very briefly. And by the way, where can you find the solution? Just go to eClass and you'll see assignment number 3 solution. So that one there contains a link to the project containing the solution file and many extra test cases to help you even to evaluate your own submission. And then there are also some suggested exercises for you. You can also take a look. All right, let me talk very briefly. Not to really get down to very specific Java detail. Let's talk about a high-level idea. So for your assignment number 3. So let's talk about task number 1. And if you recall what's really about task number 1, it's about the rank, right? So let me sketch. So let's say you have task number 1, and you're given the root of some subtree. I'll just say Tn for tree node, right? It is some node n. And then you're given 2 integers, I and j. Right, so for that one there, you're going to return all the values between the ith smallest to the jth smallest, something like that, okay? How would you solve this problem over here? So I heard about quite a good number of different solutions from you guys, but let me say, in general, there are 2 ways for you to do it. If you got other ways, feel free to discuss with me. So either you can do approach number 1. Let's say this is the input tree you're given. And let's say over here, the root of the tree is simply n, right? Over here, okay? So let me just write down the same input for approach number 2. And that one there, you also got some node over here as the root. And this will be very similar format as you will see next Monday when you actually solve the programming test 2 question. Okay? Let's say you're given this. How can you find out? Maybe the ith smallest could be here, and the j smallest could be maybe somewhere here. They have nothing to do with each other. So I would say if you try to calculate directly about I smallest and j smallest on the tree, it may not be the most effective way to do it. I would say whenever you're seeing something that's completely new, simplicity will be the key. Let's not worry too much about efficiency just yet. For the actual programming test, as long as your method terminates, you'll be okay. You wouldn't get any penalty for running, for example, n squared as opposed to n log n. You wouldn't get penalized for that. So that's the principle. I want you guys to focus more on the conceptual clarity just at this level. Okay, approach number 1. The idea would be, rather than trying to figure out like a sorting order between I and j directly on the tree, we know much better if we can somehow get a sorted array or sorted list, like a linear collection of the nodes. And then we find out where the ith smallest is and j smallest is in the actual linear collection. It's much easier. So what do I mean? Approach number one. If you can somehow do some traversal on the tree, starting from n, and you know about in pre-order and post-order. And can we do in order in this case? Not really, because it's not guaranteed to be a binary tree, right? Just remember, okay? If you can somehow do a traversal, in that way, you're going to get just a linear collection, okay? So, of course, in the actual programming test, this could be maybe some, you know what, let me just do a little bit more precise. It could be a singly linked SLL node, okay? It's going to be a chain of different nodes over here, okay? Just by doing the traversal, you have to remember the nodes themselves are going to be unsorted. Okay, it's important to realize that. Just do chunk traversal, okay? And that one there is going to take linear time because you're going to just collect each node from the tree. How many nodes do we have in the tree? N, okay? Oh, you know what? Just to also avoid confusion, let me put capital N. So the N here will be the number of nodes in the tree, okay? That's the first step, and you know how to do it. And given this, like a linear collection of the nodes, how do we figure out ith and jth? We need one more step. We need to sort it. So far, you learned about 4 sorting algorithms: selection sort, insertion sort on the arrays. You can easily just go to the lecture slides, you know, to see the fragment of code that works and adapt it to something that will work on a singly linked node. So that'd be one way, either selection sort or insertion sort. If you really want to try something more advanced, you can try merge sort or quick sort. That's something I would suggest leave as an exercise for you. Don't try that in the actual programming test. That'll be too much, okay? All right, so the next step will be we want to do some sorting. And then this one here is going to be some sort. And you can either do insertion sort or selection sort, either way. That one there is going to give you just another chain of nodes over here. That is actually sorted. What you gotta do is figure out where the ith node is and where the jth node is, and then simply try to return them. All right, so that's a big idea. I don't think this is the solution I gave to you, but this is one possible way. If you find this one to be conceptually clearer, you can do it. You need 2 steps. Step number 1, you gotta do traversal. Step number 2, you gotta do sorting. Okay? Are you guys okay about the first one? Okay. Of course, this step will be the most complicated one. That'll be a nice programming exercise for you. What about approach number 2? The principle is the same. We still really want to get this linear sorted collection, and we try to reduce the number of steps into just 1. We want to do traversal and sorting at the same time. Okay? Sounds very complicated, but it's not really. So the idea would be, we want to say, for approach number 2, we want to do traverse plus sort at the same time. That one there is still going to give us some linear collection of nodes, but this one here is already sorted. Okay? And then accordingly you're gonna identify where the ith node is and where the jth node is, for example, maybe here. And then try to return them. But now the question is, how do you exactly do sort and traverse at the same time? This is actually what the solution will actually show to you, how to do it precisely. And I want to give you some conceptual hints. What you really want to also review for this particular step, look, or I should say revisit, because that's something we cover in the class. Revisit how each step and insertion in an insertion sort would work. Right? So you really want to review about how the insertion sort can be done. Each individual step, if you recall, in the insertion sort. Insertion sort, we said that, let's say if you already got some sorted array like this is already sorted. And then you're trying to add another new element into this sorted array to grow it, right, for each iteration. In that way, where should this element go? It might go here, it might go here, or it might go here. You have to do some linear scan to see where it should go, right? So this will be what you have to review about how to do. And this is what the assignment solution shows to you for task number 1. All right, guys, are we okay about the 2 possible solutions? You can definitely try one over here if you want to by yourself. Otherwise, solution that's provided to you is following this approach, which I think is pretty nice. Okay? If you got any specific question about the Java code, let me know, and then we can talk further. All right, any question before I move on to task number 2? All right. And for task number 2, we are trying to calculate some statistics of the tree, right? So this one here, let's say you're given just an input tree. Again, right? Let's say this will be n. Again, you got approach number 1 and approach number 2. Okay, so again, you got the root of the tree. Okay? Let me talk about, excuse me, let me talk about my solution, maybe as a second approach. For the first one, let's say you don't really want to create too many intermediate tree. What you will do is you're going to somehow create the output tree on the fly. Okay, let's say this. Let's say this is the input, and this is the output. So you're going to somehow do some recursive traversal of the input tree. Let's say when you are here, you're trying to call some helper methods to figure out what should be the stats for the sum and what should be the stats for the number of descendants. You want to define some extra helper method. Call helper methods on sum and the number of descendants, for example, along the way. So on this particular node, once I know about what's the sum of this particular subtree and what's also the number of descendants of this particular subtree, I got 2 results. In that case, I can create a new node over here that's going to be a string concatenation of the 2 results from the helper methods. Okay, so that's one way. This one is not too bad. I pretty like this solution, really, from one of you who came to my office hour. Okay, that's really nice. So I just want to share with everybody. I think it's a nice solution. What I did in the solution, in some way, I would say it's not a perfect solution, but I think conceptually it's quite nice. Okay, what I do is I create, before I can even generate the output tree, I try to create 2 intermediate subtree. 2 intermediate trees. Each one of them is going to store the different statistical information. So think about, I'm going to get 2 intermediate tree. One here and one here. Okay? So I'm going to run some recursive helper method to really traverse the tree for the first pass. That one is going to generate some tree. So think about this one here, maybe n prime. And this one here is going to store the sum. And I'm going to get another intermediate tree by a second pass. That one, let's say, is n prime prime. That one there is going to give me the number of descendants. I got 2 intermediate trees. That's what you will see. And then, how do I generate the actual output tree? So this is an interesting way you can see in the actual solution. To really generate this, I have to make sure I run another recursive helper method, which is going to look at these 2 trees simultaneously. So whenever I try to make a recursive call to the left, I'm going to say to the left of this node over here, and also to the left of this node here simultaneously, whenever you try to call by value. That's something you want to keep in mind and see exactly how to do it. Okay? That's really the insight you want to build for this particular one. Let's say over here and over here, right from here to here. Simultaneous traversal of the 2 intermediate trees each one of them storing the information that we need. And ultimately, you can actually build this output tree along the way. All right? So these are the two possible flavors you can try. If you got other solution, feel free to discuss with me. We can take a look. Right? It's a very quick conceptual walkthrough about two possible solutions for each task. All right? If you got others, feel free to try. All right? Any questions before I move on to the binary search tree again? Okay? Okay, so get prepared for programming test number 2. I think it's definitely worth your efforts to really get very familiar with the recursive and also tree link structure before you actually finish the course. I think it's really important. Okay? All right, so let's now go back to binary search tree. And today, our mission is to finish that at least. And if we have time, we can go a little bit over to the last lecture series. We'll see. Okay, okay, we talk about, let's see what we talked about last time. It would be nice to have a very quick recap. So last time we dived deep into the two properties for binary search tree, right? If you recall, there is a so-called searching property. In that case, every node in the left subtree must have their key value strictly less than the key value for the root. And also every node in the right subtree should have their key value strictly larger than the key value for the root. And this property here should be applicable for every node recursively in all the tree. Basically, think about how many subtrees you actually have in the tree. You have to check this many times for the search property. Okay, that's a search property. And the second property we talk about is called sorting property. Think about sorting property is like search property plus in order traversal. Okay, so these are the two. And this one tells you if you're given an arbitrary tree, you have two ways to check to see whether it is a binary search tree. Approach number one, like what I said before, you can check to see every subtree in the tree and make sure they satisfy the search property. That's approach number one. Approach number two, you can simply do an in-order traversal of the tree and then make sure the resulting sequence of the keys is sorted in the ascending order. Okay? So these are the two properties you want to make sure you understand. Okay? And we talk about how you can implement the binary search tree using this node here. And again, what you will see on next Monday, it's not going to be this class specifically. It's going to be the tree node you did in the assignment number 3 and also in the practice test. But this one here is also worth knowing about. That's something you might be tested in the exam. So make sure you still have time to digest it. Right, we talk about the structure for the class, and then we'll talk about how you can do in-order traversal, right? And we even gave you some exercises about the return value being just just being an array list. It could be maybe array, or it could be a singly linked node. I highly suggest you try number 2 over here. It's a very good way, even for preparing your programming test 1. It can help. Programming test 2. It might help. Okay, and then we talk about how you can build a tree, right? By setting different references, and also the importance about aliasing, since we are using an object-oriented programming in this course. Definitely worth knowing. Okay? All right, that's basically what we talked about last time. And today, we're going to finish the second part of binary search tree. Now that we know the search property and sorting properties very well, and also we know about how to implement each node and build a link structure, let's see what are the standard operations we can perform on the binary search tree ADT. Okay? So we're going to talk about searching, insertion, and deletion. And we've got 3 operations to go over. Before that, I'd like to give you some very quick roadmap and something you want to always remember to check. So we talk about BST operations. Okay. Number 1, the input for each one of them is a BST, obviously. Once you know it's actually a binary search tree, you know that it satisfies the search property. That's something you can assume. And there will be 3 operations we're going to do. Okay? So 2.1, we're going to see searching. Okay, 2.2, we're going to see insertion. 2.3, we're going to see deletion. And it's so important to note, because for each of the operations we're going to touch upon the input tree, which is binary search tree, we want to be sure after performing each of the operations, the input would not be compromised for its search property. Okay, that's a very important concept. So that's something I'll keep emphasizing for each case of the illustration. So I'll put it here. Critical. The search property should be maintained or preserved in the output. That is, it remains another BST. All right, that's something I'd like you to keep in mind. Okay, that's something we'll keep emphasizing. All right, let's now go over one by one. The first one is going to be about searching. Okay, let's take a look. So given some BST node, so which would be the root, and let's call it P. P standing for like a parents. Okay, and then we want to locate a particular node like a searching. So you remember we are using the key value for searching purpose. Each node stores an entry, which will be the key and the value. But whenever we do searching, we only worry about the key. Okay? And this will be the code. I'll get there in a moment. And why don't we do some very quick example just to see. Okay, I think that'll be more intuitive for you. Okay, let's do this. All right, guys, for now, please only look at this one here. For this one, not to worry just yet, okay? I want you to, oh, you know what? I can help you with that, more focused, okay? Now, can you just do in your mind, what's going to happen if I say I want to search for the key 65? How is it going to work? Apparently, 65 is actually here. That's obvious. But what would be the algorithmic steps to actually go there? Yeah, go ahead. Yeah. Yes, that's very good. Exactly, very good, thank you. Yes, I think what your classmate said was completely spot on, but let me just, I'll rephrase it. Just give me one moment. Guys, how about this one? This one's more interesting. Let's say I want to search for 68. Wow, 68 is not even there, right? And if I want to search for 68, this is something you want to remember. A very standard way to implement the searching is, very often searching should be part of the process for inserting something into the tree. So that's why searching here, we're going to do something that might seem a little bit unintuitive at first, okay? So here, if we're doing searching 68 over here, since 68 doesn't really exist, returning null could be one possibility, or returning false could be another possibility. But we're going to do something that's going to be more useful for later insertion. Okay, how? I'm going to see that. Okay, let's now go over these two cases quickly. Okay, let's say 65. We start with this, and 65 apparently is larger than 44. That means if it exists in the tree, it must be on the right subtree, right? Based on the search property. It must be over here. Okay, so that means we must go to this particular branch. Are we okay with the first step? And it's also important, as soon as we actually go this way over here, effectively, we have already eliminated about half of the search space, okay? So this part over here basically has been eliminated. Eliminated from the search space. because we know all the nodes over here will be strictly less than 44. And 65 is not possible to be here, since we assume it's a binary search tree. Okay? And we do something very similar. Let's say we try to compare 65 and 88. In this case, we got the opposite relation, because we know 65 is strictly less than 88. So if it does exist, it must be on the left-hand side of the left subtree, right? So that means it must be here. Okay, it must be here. At the same time, you can see we are shrinking down the search space. Not only that, it is important for you to see which branch we should go. Also, you should really appreciate we can eliminate the other branch from search space. That's really important when we talk about running time later. Okay? And this one here is also eliminated from search space. Okay, let's now take a look. So we got 65 over here. Oh, we are lucky. Now, found. And return. So what we're going to return is this particular node, 65. So the search routine or search method that we're going to see in the Java code is always going to return a BST node. In this case, we return 65. Okay? Now, guys, question for you. Let's say we want to search for 68. What node should we return? Returning null is not the option. That's not very useful. If I want to search through this tree here, apparently 68 does not exist over there. What node can we return? I'll give you one hint. In the previous case, where the search key over here does exist, we return the internal node that matches the search key. Now, if the key does not exist, what should we return instead? Ferrets, go ahead. Yeah, yes, the external node, yes, it could be one external node, but it's not an arbitrary external node. It should be the external node that could be potentially hold the search key that we are finding. Question? Yes, absolutely. Thank you. Yes, I agree. Okay, so let's now do this. And let's do this process over here. So for this time, I'm not going to bother you with what space has been shrunk or eliminated. You want to do the exercise yourself. Okay, let's see what's going to happen. So we start with 44 over here. We know that 44 is less than 68 is larger than that, so we must go this way. And then 68 is less than this, so we must go this way, right? And then 68 is larger than 65, so we must go this way. And then 68 is less than 82, so we must go this way, right? You can see we are reaching down to the bottom of the tree. That's okay. And then you can see 68 is less than 76. And now we go down to this particular node. Once you reach the external node, that will be the terminating case, like a base case for searching. And in this case, you can say the search was unsuccessful. In that case, we return the external node. Okay, number one, unsuccessful search. Unsuccessful search. And number two, you want to return the external node that can store the searching key. Right? The searching key we want is 68. So potentially, the 68 can go over here. Okay? It can. So for the search method, we just return this node over here. Okay, let's summarize about what we learned from the searching, and then I'll show you the code. Everything will just be clear. And then we'll talk about running time. So whenever you do searching, okay, it can either be successful Well, it could be, of course, unsuccessful. In the case where it is successful, return the internal node with the matching key. And what if it's unsuccessful? In that case, return the external node that can store the searching key. All right, so these are the two cases, right? That's the principle. All right. All right, any question about the illustration over here? We haven't seen the code just yet, but it's good to actually talk about how it works to get some intuition. Let's look at the code, which is over here. Okay? Yeah, question? Yeah, the reason that the question was, why do we want to return this particular node? I think in just the searching process alone, it might seem a little bit weird, because if the key doesn't exist, why don't you just return maybe null? But I think later on we will see searching is very often not just done alone. You actually want to do insertion at the same time. In that way, returning the external node from here can save you some running time, and then you can simply just use whatever external node that's returned, turn that into an internal node for the value. That's something you will see when we talk about insertion. Okay, let's take a look at the algorithm very quickly, and this part here just for running time. We can do that a little bit later. Okay, over here. Okay, I'll make it more focused for you. Okay, so this will be the method we want to return, we want to define. Search. The input is a single node, and then it has some key, right? This will be the root. This will be the key to search. And then the return type is another node. And this node over here to return can be either internal or external, depending on whether or not it's successful. Okay, well, let's take a look. So here we say that if we are reaching the base case, if the current node that we are looking at is already external, in that case, we just return P. So how do we see this case? If you look at here, we start from here. When we reach this particular node, so this is external. In that case, the P that we talk about in the code is going to be external. In that case, we just return this particular node, right? That's a base case. Okay. Very important for you to identify. So this one here is base case. Okay. And then we got another base case. This base case would be when we actually got successful search. We say if the current node that we are looking at has the key matching the searching key, which is integer. That's why I'm using equal. In that case, we just return that particular node. How do we see this case? If you go back to the first example, let's say P is currently this node, 65. That one there has the matching key as the 65 we're looking for. In that way, we're done. We don't need to recur down any further. In that case, we just return this node. So we have seen the base case like this and the base case like this. Right? What's missing from the method is to see in each step, how do we make progress about should we go to the right or should we go to sometimes the left? That's what's missing. Okay? Right, so these two cases, I already showed to you the correspondence. What about these two? So these are the recursive cases. Okay? So these two are this one here and this one over here. These are the recursive cases. Right? This one shouldn't be too surprising to you. If the K that we are looking for, right? You can see the K over here, is smaller. In that case, we go to the left. If the K is actually bigger, in that case, we go to the right. Right? You can see these are the two recursive call. that we have to make. Right? A very straightforward definition for the search. You got two base cases, either for successful or unsuccessful searches, and you got two recursive cases to go to either left or right. Okay? All right, any question about the code structure here? Any confusion you might have, then we can talk about it. Okay, before we talk about running time, I want to show you one more thing. How do we see this search process run in Java code? Okay, I'll show you some highlights. Okay. Let's take a look. All right, so this part over here is what we discussed last time about building a tree. So this part here is not something new. Okay, so what I would do is, for this part here, you can definitely refer to the lecture recording from Monday. Okay, this one here, just building the tree. And this is a tree that we're going to build. Okay, let me remind you very quickly. We got N28. So this is N28, N21, and also N35. All right, so these are the three internal nodes. And also we got 4 external nodes. So external node number 1, I'll just say, EXT. And this is number 2. And this is number 3. And this will be number 4. Right? I didn't really show the bidirectional references, but that's something you know from last time. Let's see something new, which will correspond to how we did the search. Let me show you 2 examples. The first one, let's take a look at this line. Okay, this one here. Let's start with this. Let's say I got search, and then I want to start with N28. And then I want to search for the key 21. What's going to happen is I start from here. Okay, so let me see. So I start from here. And then I know that the search key 21 is less than that. So I should really go to the left branch. And once I go here, this is the matching one. That means I should really return this particular node. And you can see that one there, aliasing. The return value from this particular search has the same reference as N21, which is over here. Right? That's what it's saying. Let's see another similar running. Let's say here. Let's say I want to now search for N28. Oh, sorry. I want to search for 33. Starting from N28. So I still start from here. So if I want to search for 33, so 33 is larger than that. So I should really go this way. And then 33 is also less than this. So I should really go this way. In that way, I'm going to reach this particular external node. And that's going to be returned, right? And that way, I'm going to see the reference aliasing to external node, number 3. Okay? So this will be the second way, second result. Right, look at other result as well to make sure you're convinced. Again, for the searching process, you have to understand, number 1, we always return some non-null reference to some node, which could be either internal or external. Number 2, you have to make sure when you trace the code, you really know where to go. Either go to left or go to right. Okay? Question?
Right, so we have an external node that doesn't have, but we do have its parent node, which has 35. Is it because that the external node is on the left branch, which should be less than 35?
That's correct. That's correct. So let me just emphasize over here. So the reason that we are returning this external node, let's say rather than this, is because 33 that we are searching for is actually strictly less than this 35. So we must go to the left. And once we go to the left, there's no further internal node for us to call the recursion upon. So that means this will be the terminating case for us. So that's the one to return. And later on, once we finish searching method, we're going to see how we can integrate this searching process into insertion. Then you will see how useful this can be.
So that also means that it could have been any number greater than 20, but less than 35, and so it brought to that same example.
Yeah, it's a very good observation. So the observation was, in theory, any node that can be stored over here will be some value between 28 and 35. Do you guys know why? If you try to do in-order traversal, okay, it's a very good observation. Any key between 28 and 35 can be stored here, potentially. Because if you try to do some in-order traversal, right, you're going to somehow to say, okay, let's say we want to do in-order traversal. This, and then this, and then this. And then this, which will be 28. And what will be the next one? This one here. And then the next one will be 35. You can see this node over here is going to be between 28 and 35 in the in-order traversal. So that's why any value that's between 28 and 35 can be stored over here. Are we okay with this? Okay. Very nice. That's something I didn't actually plan to say, but I'm glad you observed that. Okay. So guys, think about this insight over here. This is very crucial. Okay. And the way to really understand it will be about in-order traversal. And of course, the sorting property. Okay. All right, any question about the searching here? We talk about conceptual working, and also we talk about Java. Right? So the next, the next topic will be, what will be the running time for the searching? Okay. Just by looking at, let's say, this diagram here. Right? Basically, we start with somewhere on the route. Every time we might go to the right, go to the left, go to the right, go to the left, etc. Until either we meet some internal node that has the matching key, or we have to go all the way down to the bottom and meet some external node. These are the two cases, right? So what will be the running time really for searching? The height of the tree. Okay, that's good. Okay. And Faraz, what was your answer? Log n? Okay. Here, it's really important. It's also on the slides. Let's think about this. Okay. Let me draw some picture over here. Let's say I'm now here. This is where I am currently. Let's say it's P. Okay. Every time let's say P does not have the match key. In that way, let's say this could be, let's say, level I. And P, let's say, not matching. In that case, we will have to go with either the left or the right, depending on how large the search key is, right? Let's say if we want to go to the left, for example, okay? If we want to go here, so that means there's one method called get left. And then we can go to this particular one. That means we're going to strictly down one level. This will be level I plus 1. Right? So that's a general process, right? And then you can think about this one here is going to be big O of 1, just this single step, which is about calling the get left method. And symmetrically, you may also call the get right method, but that will be something similar. Okay? So to really figure out the running time, you want to think about each time I might go to the right, go to the left, go to the right, go to the left. How many such get left or get right calling do I have to do in the worst case? The worst case should be if I am forced to go all the way to some external node, which will be at the bottom of the tree. That'll be the worst case, right? The worst case would be unsuccessful search. In which case, we have to get down to the get down to the bottom level. Right? It's an important insight to see. Now, if we have to get down to the bottom level over here, in that way, how many get left or get right are we supposed to do? I heard log n. I heard something called height of the tree, right? Which one should be the correct answer? So let me write down the actual critical question here. How many, let me call this is recursive case number 1, recursive case number 2, okay? In the worst case. Okay, that's a critical question. Answer 1 could be, let's say, h. Answer number 2 can be, like Farah said, log n, where n is the number of nodes in the tree. I'll give you another option, which would be n. Now, which one should be the best answer? Yeah. Say it again. Yeah, so n is the number of nodes in the tree, and h is the height of the tree. And now I'm asking basically about how many recursive case calling do we need? Each one of them is big of 1, right? But how many do we need? What will be the best answer?
I would say it's log n because it's search algorithm and it reminds me of a binary search with a...
I like that observation. Yes, I'm definitely going to compare that. So what your classmate just said was, this searching process looks very similar to a binary search on a linear array, right? Good. I'll keep that thought, and we'll need to compare that. Okay? So guys, let me tell you the answer. This is also very critical. That's also on the slides. Do you remember there was one property that we talked about before? Let's see. Let me remind you over here. Okay. You would like to revisit one of the property. Given n nodes, what will be the lower bound and higher? What will be the lower bound and upper bounds for the heights of the tree? What's the lower bound? Let's say the heights of the tree less than or equal to, greater than or equal to, right? What's the lower bound? 0, in general, right? Okay, the lower bound should be log n. The upper bound should be n, roughly. This one tells you binary search tree, after all, is just a binary tree. And its heights can range from log n to n. So when you talk about the running time of the searching process over here, it would be incorrect to say it's log n or n, because log n over here is really the best case. On the other hand, the n over here is really the worst case. And the h over here will be the most accurate answer. Now, here's a question. Can you picture yourself? Is it, let's say, given the same set of nodes, is it possible to have a binary search tree that has height n? And we have another binary search tree that has height log n. Is it possible? If that's possible, then what I just said was actually right, because you cannot just say either log n or n, because it depends on the heights, right? Think just for one moment. I do have some example to show you. I'm just trying to show you the thinking process. All right, if I show you the answer, let me recap very quickly. So when you talk about the running time for searching on a binary search tree, you cannot really say it's either n or log n, certainly, because you don't really know what's really the height. The height over here is going to determine how many recursive calls we're going to make. If you're lucky, you got the best case. In that way, we only need to do log n times of recursive call. In that case, the running time will be log n. And this case pretty much corresponds to the binary search on array. On the other hand, if you're unlucky, somehow the tree structure is like a one slanted tree, which we talked about before. In that case, doing all the way down to the bottom, it will correspond to how many nodes are actually in the tree. That's the worst case. So you got to be careful. Okay? That's really what you want to know. Question first before I show you example. Yeah, I see what you mean. You're right. Determining worst case is, okay. In this case, yes. If I say your running time should be based on n, in that way, you definitely want to say n. That would be the worst case. I agree. On the other hand, if I say now, try to be as accurate as possible about what's going to happen in the searching process. In that way, you may want to say it's h, depending on what variable you can use. If you want to use the h, that'll be the most accurate to say. If you can only use n, indeed, this one should be the one to say in the worst case. Okay? All right, let's now take a look at one example. Guys, can you convince yourself? This guy here, which is a binary search tree, this guy here is another binary search tree, this guy here is an array. These three collections are essentially the same. Well, when I say the same, I mean contents-wise. Take a look at them first before I dive into them. This page is going to exemplify what I just said, and I'll try to draw some connection to linear search on array. That's very important, and then we are done with this topic. Take a look at the tree on the left-hand side and the tree on the right-hand side, and also the array at the bottom. How are they related? Okay, I'll give you one more moment to think about, right? I think what we're talking about now is no longer the very basic about binary search tree. We are really trying to draw some connection, right? If you take the in-order traversal of both trees, they are going to end up with the same array, right? Okay, yeah, that's pretty good. So, number one, you should really know. Let's say this is, let's say node 1. This is node number 2. And this one here, let's say this is array. Okay? If you try to do in order traversal, starting from N1, it's going to give you the same as if you try to do in order on N2. And that's going to be just array A. Okay, it's going to be the same. Okay? Well, I'll let you check to see if that's really the case. Okay? So that's how these three are related. And what's more, okay? You can see over here the number of nodes in this tree. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And this one here also has 15 nodes. Okay? But the structure is very different. The height of this particular tree, right, is going to be, roughly speaking, right, is going to be the depth of the maximum depth of the nodes. So for example, if you go over here, right, if you try to, height will be 1, 2, 3, 4, 5. How about 5? It's somehow getting very close to about log n. Very close. Okay? On the other hand, if you look at this particular one, the height would be, wow, it's pretty bad, right? You can see that's pretty much slanted. In that case, you got 1, 2, 3, 4, 5, 6, 7. Okay, about 7 is close to n over 2, which we know asymptotically is just n. So what I really want to conclude on this one here, this is the best case. of searching. In which case, you got a big O of log n. On the other hand, this will be the worst case. That will be big O of n. This is why, if I ask you to really give me a very accurate bound on the searching, if I say really absolute worst case, of course it will be n, because it is definitely possible to have a binary search tree that looks like this. But if I want very accurate bound, you may want to say big O of h. So that's the most accurate. So you really want to go back here and think about these three options as I discussed. Okay? Now, question for you. That will be the last observation. And then I think you guys should really take a short break. Okay? I know that I can do binary search in this case. I can also do binary search in this case. Now, which case corresponds more to doing a binary search on a linear array? Think about it. It's a very important question. I know some of you already got it, which is good. But for those of you who haven't got it, let me rephrase the question. When I do a search on a binary search tree, it can be the best case. It could be the worst case. Now, which one of them resembles more about doing a binary search tree in a linear collection array? And remember, you learned about binary search in the makeup lecture, right? Assuming that you have done that. Okay. Now, which one? You can say none if you don't see any correspondence. Anybody? Mario. The one on the right. Over here? Okay, I'll hold that thought. Okay. Okay, let me tell you why it wouldn't be the right one. Let's say this. Let's say I'm searching for 97. And I will somehow start with maybe the middle point. Right? And then I know I should go to the right half. And then after that, I know that roughly speaking, it will be 82. Right? And then I should go to the other half. Right? And then eventually I can get to 97. That's basically binary search on the array. Each time when I do branching, either left or right, I can truncate about half of the elements, right, for consideration. Is it the case for this one here? Well, think about it. For this one here, if I try to search for 97, first of all, I should go here. For that one, I agree. Just this step alone, I can truncate this particular half. I agree. But when you try to go to the next one over here, it's not truncating the half anymore. It's just have to reduce nothing. Because you got to keep going, keep going, keep going, keep going, keep going. And this will be the matching one. That one is actually not really corresponding to it, right? Can you follow my point? So this is not really corresponding to this one here. The searching process is similar, but the running time is not really. Because we know when you try to do a binary search on a linear array, it's always log n, always. Okay? All right, so the answer should be this one here. Okay? So what you should really convince yourself, if you haven't, is to see why this one here is really correspond to this one here. Okay, a final remark. The best case of performing a search on a binary search tree, which is log n. That one nicely corresponds to if you try to do a binary search on a linear collection. Because for both of them, each time either you want to go to the right or you want to go to the right over here, you're basically truncating the other half, which is about half of the nodes or elements. That's something you want to really draw a connection to. Okay? And one more question, and then we can take a break. If we know that doing a search on a binary search tree is no guarantee about reaching the log n, what should we do to really make it always log n? Yeah, somehow, yeah, you're right. Maybe we should really try to construct a tree such that the height can remain to be log n. That will be the topic for the last part of the tree. Not today, possibly on Wednesday. Okay? Yes, question? Yes. So what we're going to talk about most likely next Wednesday in our last class will be we want to somehow introduce another idea. It's called balanced binary search tree. We want to make sure our binary search tree is such that the height is bounded within log n. We don't really want this particular occasion to happen. So in the exam, right, whenever I say, now I want to do some search on the binary search tree, you always want to look for the hints. Did I say we can assume the binary search tree is balanced? If I said so, in that case, you can assume it's going to be log n for its height, the minimum. If I didn't say that, you cannot assume it. In that case, you can get down to ON over here. All right. So if you go back to the slides, you will see that that's basically what we talked about in the last maybe half an hour or so. All right. That's a diagram I explained. And also, it's important for you to look at the derivation over here, which I also discussed. And this will be a nice table to summarize about how you can compare the best and worst cases for doing search on the binary search tree, and also what will be the tight bound for doing search on a sorted array. Right? So these are the things we want to review. All right, any question? If no, why don't we take a short break and take attendance? I think we still have some time, a little bit after the break. Okay. Okay, you can get your device ready, and then we can take attendance. Okay, you can check in. Okay, we're taking attendance now. If you cannot really log in, we'll check in. You can come forward. Okay, everybody's good? All right. Okay, awesome. Thank you. Yeah, guys, take a 2 minutes break, and then we can use another 15 minutes or so to finish up the class today. Okay, take a short break. Yep. You mean reference aliasing? That's what you're talking about. Yes. I think, yes, conceptually, yeah, I see what you mean. Come over here. Yeah. I see what you mean. Very good thought. I think that one is more like an implementation level issue. You basically, conceptually, we think about, it's easier to think. Each one of them is like a separate external nodes. But, of course, if you really want to have, to save the space, you can say there's a single external node, and every one of them is simply pointing there. Yes, but I can tell you that you will have some slight trouble when you actually want to do insertion, because later on we'll see after the break. Let's say this. Somehow I return this node over here. And if I want to somehow turn this one into an internal node, but that one there is really the same reference that's referred to by everybody else. Is exactly, that's aliasing problem. So I would say, unless you have some mechanism to say, okay, if I really want to turn this into a new node, I need to create new objects on the fly. So that means you wouldn't occupy all the space always. You just create a space when you need it. It's completely up to you. Good thought. Yeah. I think it's just insertion there, you have to be you gotta watch out. Otherwise, when you change, maybe this particular node here is gonna impact everybody else. Okay. Good. You're good? Oh, okay. All right, guys, 1 minute, and then we'll continue. Okay, we'll start in just one moment. Okay, let's start again. Okay, we got about less than 50 minutes. I'm pretty sure we can do something. Okay, if I really cannot finish deletion, I don't think I can, but we can definitely carry on from next Wednesday. Okay, let's take a look. So, what about insertion? As I kind of look ahead together with you, insertion is going to be very closely integrated with the searching, which we discussed a lot before the break. Let's see. Let's say I want to insert a new entry, both the key and the value, into some given binary search tree. What's going to be the procedure to really make this work? Okay? You can look at the slides for exactly what to do. Right? Very simple pseudocode over here. Okay? Just in words. And of course, it will be optional exercise for you if you want to implement this in Java. You got all the infrastructure you would need, which is a BST node. But let's see some example to see how that works. Okay? And you can see that whenever I want to insert an entry, I need to pass definitely some key to search. The new entry should have 28 in this case. And the new entry here should have 68. And typically, if you want to do insertion, this key should be non-existing, right? Should be. However, there will be some other practice in which case, if you try to insert a new entry, but the entry's key is actually some existing key, in that case, you just want to replace the corresponding node. But that's another way to do things. But let's see something a little bit simpler for you. Okay? Let's say this. If I say I want to insert a new entry, the entry should have key 28, and we're going to search for this one here first. And the data value, let's say a string, will be Suyang, for example. Okay? What should we do? So step number one, as you can also check the slide later, we're going to do a search. Okay? So we're going to start with 44 over here. That one there, we know 28 is less than that. So we should go to the left. And we know 28 is larger than 17. So we should really go here. And we know 28 is less than this. So we should really go to over here. Right? So this is what we have. Well, actually, I do have some case for you. Okay? So in this one, you can see 28 over here is an existing key. It's kind of up to your implementation. If you want to say, I don't want to allow any insertion of the existing key, I don't want any replacement, in that case, you can throw some exception. But I believe in this case, the intention is you don't really want to throw exception. You just want to do some replacement. Okay? I'll just say here. Otherwise, it could be misleading. Should be non-existing. Otherwise, do some replacement. Okay. So you can see this 28 over here should be returned. Returned by the search method. Right? This particular node. Let's call this n. Once you get a particular node from the search process, right, we talk about how you can return the internal node, and then return by the search method. That'll be number one. Number two, you're going to set n's elements to, in this case, Suyang. Okay, let me recap. In order to insert a new entry into the tree, you got two cases. Either the entry's key already exists, in which case you don't create any new node. Whatever internal nodes for successful search that's returned, you're going to replace its element value by whatever value you have. And you do have the set element method for the node. Okay? What about the other case? Let's say the node you want to insert into does not have its key existing in the tree. Number one, we know that it's going to be an unsuccessful search, in which case we're going to have some external node back. Let's see. So what we have is, let's say here, 44, 68. should really go to the right, 88, and 68 should go to the left. And then 68 should go to the right. And 68 should go to the left. And again, 68 should go to the left, right? So this will be the external nodes that's going to be returned. Okay, so number one, so this particular node will be returned by unsuccessful search. All right, so that's the one. And once you return back this external node, what should you do? Well, since our intention is not just to do search, but also to set the data value. So what we'll do is, number two, store the key, which is 68, and elements, which is UNA over here, to this external node. So essentially, we are transforming this external node from an unsuccessful search into an internal node. That's what we're doing. Okay? So conceptually, number two is like this. So that means we're going to have a node over here that's going to have 68. And of course, also store UNA over here. And then that one there is actually going to have two external nodes. That's kind of the implementation detail you have to watch out for. Okay? All right, let me recap. For insertion, in the case where the key exists, you get an internal node back, and then replace its data value by set elements to the elements. Set case number two, if the entry you want to insert into does not have the existing key, you're going to have some external node return back. In that case, try to store the key and the value into that external node, which essentially transform that into an internal node. Okay, so these are the two cases. Okay? What about the running time? What is going to dominate this particular insertion process? Yes. Searching. Yes, exactly. Because either you got some internal return back, or you got some external node back. Once you got these node back, all you got to do is to set the elements or set the key. That's really big of 1. So the searching process is going to dominate, which would be big O of H, right? So the running time is going to be big O of H, which is about the searching. This also tells you that it's actually very convenient to have the external node return in the case of unsuccessful search, because you can easily turn that into the internal node accordingly. And the running time will be big O of H. Why big O of H? Because you can either have some lucky case of log n, or unlucky if you've got n. In that case, we do need some extra property called balance property, which we'll talk about later. Okay. All right, that's about insertion. Any question? Ferris? Big O of H? I would say big O of H is a very tight bound, because H itself can vary between log n and also n. So I would say H over here, you should really know that. Yeah, it's more like a very more tight, more accurate. So we know that H over here is in between n and also log n, based on the property before. So to really say that about the running time, you can, if I really say the absolute worst case in terms of n, it would be this case over here, linear. But if I say now, try to express the property more accurately, in that case, it will be H. And H itself can be either from here or here. Right. Yes?
So, but one thing I think I want to know based on the recurring theme is how do we determine what our root node is? Because
Sorry, say that again. I didn't quite.
how do we determine or select our root node? Because in the previous example as well, depending on the root node that you select, it could greatly affect the
Yes, yes. So I think, okay, let's say given this particular tree, right? You always start with the absolute root. And whenever you try to, let's say, make it to the left, in this case, you have to make the root of the recursive call to be the left child, right? That's why you keep making recursive call. Yeah, so if you look at the code over here, let's say over here, right? We say that when we try to make a recursive call, the root of the subtree that we're going to work on right now can either be the left child or the right child. That's how we get down one level each time for the searching.
But what I mean is, for example, on your slide after this one, yeah, it's for, so, let me get back to
Yep.
yeah, this one. For here, on the right, for N2, we start at 54. For N1, we start at 44.
Okay, so this one is a different problem here. This one is to say, depending on what input you're given, in this case, the root of the tree happened to be 44, and this one here happened to be 54. So these two store the same elements, but they actually got very structurally different. In that case, if you're lucky, you're given this kind of tree, it's balanced. You're going to get log n running time. But if you're unlucky, if you're given this kind of tree, you'll get linear time. So this is just to say different scenario you might run into.
So your root 0 for your relative average.
Yeah, in some ways it's arbitrary, right? Because you cannot control what input you're given. What you should really what we should really learn about next time will be to see how we can maintain the balance of the height of the tree. Okay. All right, got about 3 minutes. I think we can do about 1 or 2 cases for deletion, and then we're done. Okay, why don't we do a little bit more? Okay. So that's about insertion, big of H. And these are the 2 cases we talk about. And you may just want to try to implement this, on the BST node. Highly recommended. Okay. Deletion. So there are basically 4 different cases for deletion. I would suggest we do the very simple 2 today, and then we can finish them off pretty quickly next Wednesday. Okay, let's go over case by case. And all the slides are already there on the lecture site. You can feel free to take a look. Okay. And we're still going to do some search. Let's say I want to delete the node with this particular key. And I want to know where that node is. And then I'll do things differently. Okay, let's run just over a couple of cases. We got 2 minutes. Should be good. Case number 1. Let's say you try to do some search on the key you want to delete. And the return node is actually external. What does that mean? You want to delete something that doesn't exist. Is there anything for you to do? No. Trivial. You're lucky, right? So case number 1, show to you right away. Let's say over here, I want to delete from the tree 31. Okay? So I will start with here. 31 should go to the left. 31 should go to the right. 31 should go to the left. And 31 should go to the right. And 31 should go to here. So that will be the external node. And of course, you can think about you really want to delete this particular node, but there's no point, right? In this case, nothing to do. But the running time will still be big of H, right? For the searching. Okay, so case number 1, nothing to delete. But the running time will still be big of H because of the search process. Okay, easy case. Okay, let's do one more case. Let's say this. What we got returned is an internal node. That means the key does exist. In that case, what should we do? Okay. Let's say we want to delete 80. Okay. And let's now do the same search process. Less than 80, so we should really go here. And 80 less than this, so we should really go here. 80 larger than this, we should really go to here. And 80 less than this, we should really go here. 80 larger than this, we should really go to here. So this is the one that we want to delete. And now, what should be the process to delete this? In some way, we're also lucky because in this case, the node has, you actually have no overhead of deleting it. can I just remove this right away? I don't really need to look after any subtree that's below. So what we're going to see on Wednesday, if somehow the node you're trying to delete has some very arbitrary subtree underneath, you cannot just delete it right away. You have to do some a little bit more complicated operation. Okay? I'll write it down, and then we should be good. So this one over here can delete this right away without worrying about any left subtree or right subtree, because you can see they are simply just external. And the running time will still be big O of H. Right, so these are the two simple cases. What we're going to see on Wednesday, there will be cases, let's say, for example, how do you delete this particular node? Well, that's tricky because I got some very complicated left subtree here and some very complicated right subtree over here. How do I delete that? I cannot just delete it directly. You got to do some massaging about the tree. All right, guys, thank you. And I will see you next Monday for your programming test. If you got any question, reach out. Take care.